First of all, I can't tell you how glad I am to be here, and it's not just in passing. I actually have a suggestion for you to increase your funds, your research funds. When you get visitors, measure their IQ before they come in, and then measure it as they go out, and you should charge per unit. And I'm glad you did not do that before I come, because based on the half day today, I would go bankrupt if you implemented that on me. But it's an incredible institution, and you're doing a great job. I'm also embarrassed to say, for all the work I've done over the years with individuals and great researchers from national labs, this is the first time I visit a national lab. So if it's going to be first, it better be the original, which is why I'm really glad to be here. I can also tell you, and many of you know that whether you have been a veteran in this area or new, there have never been a time over the last 70 or 80 years since actually the Edison era, where the energy industry is so full of challenge and opportunities and excitement as it is today. Never been a time like this on all sides. And for you who are just starting, the good news is there is no expert in many cases, so you're not lagging people like myself with gray hair. You're just starting just as much as we are. And for those of us like of my kind of generation or around, we're just glad to be part of it and be making the transition and make sure that we do the transition right, so we can all, at some point of time, we look at it and we say we were all part of it. So all of these things, as I speak about it today, it is not just a simple talk. I speak about it with passion based on what I just shared with you. The utilities of the future, for a utility to be successful in the future, they really have three, in my mind, three things that they should be focusing on. First, sustaining what they have in terms of the facilities, making sure that those facilities and infrastructure, existing infrastructure, operate well and operate right. Second piece is technological innovation. And those who are going to succeed would have to have competitive edge, or if they rely on monopoly, they will never make it, and not too long from now. And the third of it is customer loyalty. And you can see each one of those you can think about as a bucket on its own, but when you get into the details of it, you'll find that they're all related. Now, that mixed with all the innovations on every side of the industry, from a supply to infrastructure to demand, on every aspect, that present the excitements and the challenges that we are all facing today, and we're glad to be part of it. In most cases, when I speak on, in most cases when I do, when I speak, in most cases I try to leave behind me, or leave after I leave, with at least a reasonable level of consensus. I'm going to wait for just a minute. So in most cases when I make presentations or I make speeches, it is usually to groups where I try to leave behind, after I finish, a reasonable level of consensus. Frankly, in your case, I want to leave enough controversies, because that's what you work on, and that's what you debate. So I will try my best to do so. Also in doing so, I'm just going to have to make a declaration that that is not necessarily all the time, or everything I'm going to say is the position of the ISO, if it is that controversial. And if it is too controversial, it's not my views either. So in any case, I'll try to generate more debate as much as I can. What is the ISO? Just a bit of a publicity. We are the grid manager in many ways. We have, our core responsibilities is we operate the grid reliably. So we are the custodian of the grid reliability of the state of California. We design the electricity market. We operate the electricity market, just as we operate the grid, and the two just go hand in hand. And we're responsible for the long-term planning of the grid. We facilitate day-ahead market, real-time energy, and ancillary services. Ancillary services all support the services to make sure that the quality of service is appropriate or according to standards. We provide open and non-discriminatory access to all players to facilitate a competitive wholesale market. We are regulated actually federally, even though we are a state entity, but we are regulated federally because it is wholesale and it has to do with interstate commerce. We're governed by a board of 5 appointed by the governor, nominated by a large group of stakeholders. The list is given to the governor. The governor nominates, and it is confirmed by the state senate. And I am delighted to have 2 of the board of governors in attendance. Chris Hafner, who you know, right here in the front, and the chairman, Mason Werrich, from the board of governors of the ISO. I can tell you also that if you want to have the title of governor, you can run for a governor of the ISO and you don't have to spend any campaign money. So we call them, and here we saw Chris and Mason, but in our world we call them Governor Hafner and Governor Werrich. When we talk about the governor of the state, we say Arnold. Yeah, it's interesting that this is my 6th year in the ISO. And as I came to the ISO, actually, Mason and I started at the same time. And I can tell you that if there is few people behind the success of how we came from the misery of the energy crisis to where we're at today, Mason would be one of very few who supported this and supported me personally. I actually have a question, interesting. So as I came in 2005, moved from British Columbia to California, I also had, about the same time, I had a newborn. So my wife and I had our first son. And I was having dinner with the chairman of the commission in a very noisy restaurant. Well, people were around. And he asked me, because the board at that time that Mason came in was a new board. So he asked me, like talking about big table noise, and he said, how are you coping with your new board? And I heard it, how are you coping with your newborn? So I said, actually, very cute. and I said, and you know, at this stage of their age, they sleep most of the time. They only wake up when they're hungry or wet. And then he was looking at me and I said, I'm talking about your new board. And I heard that newborn again. I said, what the heck are you think I'm talking about? That's exactly what I'm talking about. And of course, people around the table were jumping up and down, those who knew and those who didn't know. But it's one of those memories of coming here with a newborn and a new board at the same time. I would never do it again. So what we do in terms of volume, the state facilities in terms of megawatts capacity is about 55,000. And part of the challenge, and it will even be more challenge into the future, as I'm going to talk about later, is that this state, different from any other part of the country, and even different from any parts of the world, we import about 25% of our energy needs, this is electricity needs, from out of state. And that has been a tremendous opportunity for this state to capitalize on the diversity of resources and prices in the region to make up the whole portfolio that is needed by the state. So within the state itself, there's 55,000 megawatts of generation. And you look at the demand, so far the peak demand has been over 50,000. Of course, if we have only the 55,000 versus the 50,000, it would have been a very tight situation. But the fact that we have 25%, keep in mind that they are not always certain until the very last minute, most of them. That gives us a challenge, but also give us opportunity. In comparison, let us take Spain, for example. And I'm going to talk about Spain and California later on, because Spain is a leader also in renewable resources policies. Spain has very similar to our demand, 45,000 megawatts or so in terms of demand. They have 95,000 megawatts of generation in Spain. So they almost have 100% in terms of reserve or planning reserve. So you will hear a lot of time in here when people talk about, well, Spain does it, Spain did it. It does not mean that it can just as easily be done here just like it is there. The challenges are different and the situation is different. They also have a lot more hydro that they can rely on in kind of fluctuating up and down to balance the intermittency of renewables. We operate about 25,000 circuit miles of transmission. We serve the 80% of the people of California. In terms of serve, we say on the wholesale side. And that translates to about 230 billion annual kilowatt hours. Our market, we have a day-ahead market. There's long-term contracts between suppliers and the suppliers, meaning the generation supplier versus the utilities. There is over-the-counter. There is shorter term, a month, a week. And there is, when it comes to the day ahead, this is when it comes to clearing on our market. We also have real-time market. And that real-time market is 5-minute market. So if you come and visit our control room, you will find the ticker just like you have in the stock exchange, where those prices are updated every 5 minutes. Just to give you an overview of what those prices are, we price over 3,000 nodes or points around the system every 5 minutes. And that takes care of tens of thousands of bids every minute from generation and also from the demand at the same time. It runs an optimization program based on mixed integer programming, which is one of the first. This is the first time that it is being used in that application. And it actually, that sophisticated program runs in about 25 seconds out of every 5 minutes interval to publish prices that people respond to. And the whole idea is that those price signals send signals that would indicate certain congestion point or also price of services that we need at any given point of time. The overall wholesale market volume of California in a year is about $30 billion, of which what goes through our market, which we settle at the ISO, is about $7 to $8 billion currently. That's what we settle. But every transaction, whether it's actually clearing our market or not, every transaction has to go through us. This is for the purpose of making sure that everything runs reliable. Now, as I said, the title of mine is striking a balance between reliability, cost, and environment. And historically, even though you say, what was the balance? Actually, there was always imbalance, frankly. And it depends on the time. It is usually pushed by emotions. So for a long time, sometimes it becomes reliability and sometimes it becomes cost. And they were never a balance. It's just depending on the time one takes over on the other. So for example, I think it was late 80s, early 90s, when I was a transmission planner and I was in charge of a transmission planning group. To make a justification for a transmission project or for any project, on a reliability point of view, we were forced to calculate how much is reliability worth to the consumers? How much is it worth to the public? What is the cost of interruption? So what I did at that time, I knew a lot of smart people, and the University of Saskatchewan, under the leadership of Professor Roy Billington, took a national Canadian study to actually determine what the value of interruption is, or the lost value of interruption is to consumers. And he did a good report that has, if it is interrupted by 1 hour, it is this, and if it is 2 hours, it's like $5, and then the last one, the biggest one, if it is for a day, it says it's $200 per person affected. And then at that time I said, just a second now, you're telling me a whole day of interruption, the impact is $200? I said, according to the data and that we can gather from everyone, that's what it is. It's range between 100 to 200, but it's not higher than, we could not justify more than 200. Now you can imagine myself that if I go to a commission now saying I want to build a $1 billion project because of an issue that happened every long time, and the impact of that would be $200 per person, I don't know how many commissioners will agree that I can go on with that project. So I almost want to kill that report, but I just put a lot of qualifiers in it that, it doesn't cover this and this and that. Until 2003, the Northeast blackout. All the information that many of you still remember, it said the cost to the public, to the cost to the society, was between $5 and $10 billion that one day. And it impacted 50 million people. I said, oh, now I have the data. I divided $10 billion by 50 million people, I got $200. Okay, now I said, oh, look at this. Now, after the 2003 blackout, the message was never again. And I was actually fortunate or unfortunate to be, for a whole 1 year, on the steering committee of NERC to make sure that we come with our recommendation that this thing doesn't happen again. We implemented, and we're still implementing, a lot of stuff on the standards and on the cost to make sure that once every 25 years, a situation like 2003, where the average was $200 per person, doesn't happen again. And that is now where, okay, obviously, reliability, people have very limited tolerance for a situation like 2003. Even common sense says if it doesn't happen, if you sit like this and say, how much can you justify in a situation that comes every 20 years where the impact on you is $200? We say, pfft. And when it happened, everybody says, never again. And all of a sudden, reliability in that case in 2003 was heavy. Before 2003, it was cost-based, how much you can justify. And now even the implications that came out of 2003 was a very expensive program all over the country to make sure that it doesn't happen again. And everybody's realizing now that the cost is very high. So we went from one extreme to another, and it looks like we're never at an equilibrium where we say the two are really balanced. Well, as we struggle with that balance, or the point of balance that we can hardly find, came a third player, which is the environment. Now we have to balance all three: reliability and cost and the environment. Today, probably if I say which one is heavier, I would say environment. All the energy policies are now driven by environmental goals, climate change, and limitation of global warming. It is getting much more complicated. Adding that dimension to it does not make it like 1.5. It is almost more than an order of magnitude. It actually combines societal value from the environmental side that you can hardly put dollars in, at least until the costs become unbearable for people to feel it firsthand, monetary value, and service quality. Now, what are we doing about it? Now, the solution for it seems to be renewable resources and energy efficiency. Energy efficiency is has a long history that is largely successful, especially in California. The renewable resources is new, and it has its own challenge. But right now, for now, these are the two main ones that the electricity industry is using to limit emission or to have a reasonable, good impact on global warming. 10 years forward, if you look at the policies of California at least, it is more of the new, meaning more renewable and more efficiency, but also the piece that is missing, and I'm going to actually highlight that in the rest of my presentation, you also have to have more of the old. When I say more of the old is, there would have to be facilities of the old kind of types, which is the gas-fired and the hydro or whatever, to back all the intermittency and the uncertainty in the supply on the renewable side. Now, 30 years forward, and we're going to touch on that too, it cannot be more of the same. What would it be? Well, we'll see. Now, what does California, now all the programs in California that actually tackle all of this, the first program is so-called 1 million rooftop photovoltaics. The governor had done that about 3 years ago, and the commission approved it. It's about $3.5 billion of subsidy for ratepayer subsidy or contribution to subsidize 1 million rooftop in the state. The problem is that you see when that is kind of facing a lot of challenge. First of all, not too many people did the math, not actually math, and for you, you know what math is. They did not do the arithmetics. So over 10 years, 1 million, you divided how many per year and all of that stuff, you come down to anywhere between 200 and 300 homes per day. That's what you have to do to achieve that 1 million. Well, coming with the slum in the real estate industry, where not too many new homes, that program did not go too far and is translating into larger kind of commercial rooftops. And it is basically many of the utilities to capitalize on the opportunities, or some of the utilities, if not all of them, are leasing rooftops and installing the facilities on top of it to make up for that, for that target. The second one is a multi-billion-dollar investment in so-called smart grid. And smart grid is a great concept. I'm going to talk about it later on, and somehow does it kind of inject into the success story of the success potential of many of the initiatives. But unfortunately, most of the billions that are being spent are on so-called smart meters. And the smart meter, starting a smart grid, which say, let us start with the smart meter first, it is really like finding, kind of a naked person say, the first thing I'm going to do for you, I'm going to buy you shoes. It's before you even start with what it is that is needed first, before you can get into what the meter would do. It is not a meter, even it should be a device, not a meter. And it went, and it is going, unfortunately, I can't even stop it as a wave. So we kind of are trying to leverage, okay, what's being spent, quickly try to put the standards quickly at least before the second wave of implementation come in. And the most importantly is, what is the vision? And again, part of the improving my IQ this morning, meeting with Mary and others, I think you have a great vision of what a smart grid should be and how it relates to, how it actually connects the supply with the demand all on one pot. I had a smart meter installed in my house. The person knocked on the door, and I opened the door. He didn't know who I am, and said, I'm actually here to install a smart meter for you. I said, great. So he just put it in, and then I went outside to see what he's doing. I said, so where is the smart? He said, here, this is it. I said, so what does it do? What would it do for me? He said, oh, it will just read your stuff, and then the utility will know about it, and they don't have to send anyone to read it. I said, that's all? I said, about all, yeah. I said, but listen, I'm actually reading the papers and things, and they're saying it can do a lot of good stuff in there. He said, nope. So just a minute now. They say it can actually I can do stuff with my air conditioning and the wash and dry. I said, no, it doesn't. Thank you very much. I'll just go. So even from a point of education and what it would do, the installer actually was telling me that that's all it can do. But unfortunately, the sad thing is, in the beginning and for quite a while, until we actually, I hope that is not for too long, that is the, what the impression is of what a smart meter is. But there's a lot of millions of it. Even if you look at most of the money from the stimulation funds are going in smart meters. Some of it is going in synchro phase or what have you, which is a good thing, but a lot of it is smart meter. There's another initiative, it's called banning one-through cooling technology in coastal plant by a certain time. Now, this is 30 to 40%, actually it's about 40% if you include all the nuclear, of the of the plants, of the facilities in California are cooled by the so-called once-through cooling, where they take water from oceanic water, it cools, and then throw it back in at a higher temperature in the ocean. Now, of course, that would have an impact on marine life, which is what the environmentalist issues are. And federally, about 20 years ago, there was a legislation that passed to ban it, but they didn't say when. And it has been struggling, and California wants to be the leader in it. But it is impacting 30 to 40% of the fleet in California. Well, the fleet is tight to start with. And here is now what the struggle is. Many politicians, many members of the public believe that, well, we're going to have solar, and we're going to have wind, and we're going to have all of that good stuff. We don't need that other stuff. Get it out of here. And to actually get them to understand the complex issues associated with having a system, operating a system in a reliable way, would need exactly these same facilities, and I'm going to show you even more of it, to do something else. Is not there yet, is not well understood yet. If we do that, by the way, if that is implemented, the cost could get just to that one component anywhere between $20 and $30 billion cost of replacing or relocating them. The next one is $1 billion a year investment over the next 10 years in energy efficiency and, of course, energy conservation that has always paid well, and the investment is well spent. And one of the two bigger ones, which is the 20% of energy supply renewable by, it used to be 2010, now it looks like 2012, and we're all ready for it for 2012. And then one of the other big pieces is related to air quality or CO2 emission level rolled back to the 1990 level, and that means reducing it by 30% by 2020. And on its own, it's a kind of pushing the target more, the 20% to 33%. But in large part, that one, which is achieving 33% of energy supply from renewable, would be about half of what is needed from the electricity industry to achieve the CO2 emission rollback to 1990. So that makes the color of the state moving from gold to green in totality. Okay, now, how does those things, all of those things that I put on the map, if you do each one of them on its own as a target, you will get a disaster. You will get probably more than a crisis than before. But the key is that they all have to be integrated. So when we say ban through cooling or restrict the operation of the thermal generation to such and such, if you do not do it in a coordinated way with the implementation of renewable resources, then renewable resources on their own will not be able to operate reliably and support the grid. So the more you restrict certain facilities that you think they're hurting the environment, in part, you are not going to be able to support the implementation of the full scale of renewable. And that is really the key that we're trying to get people to understand, and your help in that will be tremendous. We've talked about it this morning as to how these things fit in one. And this is where the ISO, I'm proud to say that the ISO played that part, because all of those initiatives, by appearance or by the sound of it, are combination of climate change policies. But actually, when you look at them, they also, in combination, give you the grounds for energy policy, whether on the state or the national level. Sadly to say, there is no national policy on energy now for a long time. And any time, come in a congressional session, as you know, any attempt to actually establish one, somehow it doesn't get to the top of the list as a priority. Now, I'm going to kind of use certain terminologies, and before I kind of try to wave hands, I'm going to make sure that I explain what I mean by what. So when we talk about the impact, then I don't lose you, hopefully. First, I'm going to always talk about load following. What is load following and where it comes from? In general, like historically and even today, the generators, when they submit to us their information, they give us the so-called hourly dispatch. So they tell me for 1 hour, this is what you're going to get. For the next hour, you're going to get this, but hourly. And then when it comes to real time, past that hour, we do something that is called, the dispatch come in 5 minutes. Because the difference between the load or the demand, the green one, and the red one cannot stay the way it is. Otherwise, you get problems with the system, as you power engineers know. So it has to be closer. So the hour dispatch is basically refined by 5 minutes dispatch as you go. Now, the difference between this 5 minutes and the demand is what we call you trying to follow the load. But remember, in this picture, the only variables are the demand, and the control is by the generation. Now, later on, we're going to talk about now the big variable now that the resource, when you have renewables, there's big variability in the resource as well. And how would that affect the situation? So that blue area is what we refer to as load following. Now, you get to something that's called regulation. Now, even with that, now that you had followed, now the difference between those even refined and the actual load, which is now another micro level of control, is referred to as regulation. Again, if you look at this area that we try, like right now as we speak, it is happening that all the job of the operator is to balance things out, that in every instant of time, the demand and supply are in balance. So here, as I said, the change is basically the load is the one that's changing, and you're kind of making the whole fleet try to change in different times, from an hour to 5 minutes to within the 5 minutes, to make sure that the two are balanced. Now, keep in mind that later on now, when I talk about how would this picture change now, when the supply side is also reasonably unpredicted, and it is not flat, even within a 5 minutes or an hour, never mind is predicted. So now when I talk about load following a regulation later on, you know what I'm talking about. Now, this is actually real data, so, and sometimes it is scaled to make the point, but based on real data. So you talk about here, like for example, here's a wind, and wind blows at early hours and late hours of a day. So this is at 24 hours. And solar come at certain time, jump up, stays, and then come back in a very sharp way. If you don't consider the solar at all, as the wind dying down and the demand is increasing, then the rest of the fleet would have to respond to two things. First, that the demand is growing, and part of the supply, which is the wind, is decreasing. Remember, in the past, or as we do today, it only responds to the demand increasing. Now, when you have wind, they would respond to demand increasing and wind disappearing. So obviously, they would have to go do more within that short period of time. Now, some people think that solar will help. It would help probably at this area, where the wind is not there and there is solar there. But at this point, it makes things very interesting. That now the fleet that used to follow the load and the easy decay of wind, in a way, if you add solar to it, now it would have to do exactly that in this period of time. And then when the solar come in a sharp way, it would have to run down in a very sharp way. And then as this is stabilized, the demand would have grown at that time. It would have to jump up again, back again. So you could see now we have a fleet that is going up and down in huge amounts within a short period of time that did not do in the past. And that is the kind of support that an existing fleet have to do even more than it did before to support so-called renewable. Of course, at the tail end, it is the other way around. Now, solar with wind, you could see that in these cases, in the beginning and at the end, it makes things worse than wind alone. But in between, it makes things better. Now, that curve, as much as it looks, you might think it looks great, but if you look at average, this is typical now, typical meaning simulated. And I'm really proud of what we've done at the ISO to simulate what would actually happen under various levels of renewable penetration, so we can understand what is needed, so we can make sure that we're prepared for it in the operation side. So this is a case where it is a certain date, a particular day of simulation in July in 2012. What we do is we take data from what we have, we scale it up, we do the simulation based on time of the year and the certain days and so on to give you what you might find in a case like this, in a summer day like this. And you can see that in a case like this, here's the demand, the blue one. The wind typically is like this, not typically for that day. That's an average. And then the solar is like this. So you can see now that here is the demand. Now the wind is coming like this. The rest of the fleet will have to, at this point, to actually come up to do two things. Make sure that it is following this, at the same time also compensated for this decay. Until this point, where this is coming up, it will have to go down again. And then once it is flat, the demand is still growing, it will have to go up again. So that's a kind of a date in the summer. That's an average. Within the average, you see that now the volatility, which is with what we call the whisker curve, from a minimum to a maximum, you can see how wide variation it is within the hour in a day like this. And this is 2 standard deviations of that statistical data. You look at a different time of the year, which is like a fall, and it's kind of flatter, at least in the morning. Solar is not as predictable, even, and we'll talk about predictability of solar later on. And wind goes very heavily or much heavier at later time of a day in the of this. Now, I give you average, but within the 24 hours, here is what I was averaging. So the wind, even though all people talk about wind as an evil, but solar is actually much more challenging. And predicting wind is one thing. Predicting solar is a much more significant and much more challenging issue. In fact, even for us to be prepared, we have reasonable amount of data about wind. We have very little data about solar. There's a lot of information, a lot of research now on solar tracking and what have you, and it's just the cloud and where they are and what the intensity of it is to predict how they change. But the red is an actual solar within a day. So what I showed you average, when you average this, it looks nice, and they say people, it's sunny, but it only takes a passing cloud to get that sharp. Now, those sharp change represent a huge duty on the facilities that are supposed to respond to this and that same speed. We never faced this before because we were responding to demand change, and demand change were never with that magnitudes of the 1,000 and that fast. And if you go actually, this is in the whole day. Now, if you look even within an hour, you find also that the change are within the hours and within minutes are even more challenging in the solar. The wind is a challenge, but the wind on its own is not as, well, it is significant, but it's not as significant as the solar side. Now, keep in mind, again, my job is to balance demand and supply by the split of a second or by second. Otherwise, I'm violating major standards, exposing the system to major problems. So, and that is giving you now the issues with controlling or operating a grid or a system like ours with these kind of variables. Now, we say, how big is that? Remember I said that 55,000 megawatt of generation is what's in the state? The 33% portfolio translate into 28,000 megawatt nameplate capacity. So we're talking about now 28,000 megawatt of nameplate capacity of that nature in a 55,000 megawatt system on a demand close to 50,000 megawatt of demand. Compare that to Spain. As I said earlier, Spain has 45, but they have also a lot of hydro, and they have 95,000 of installed capacity of other resources. Another area, and I was getting to the forecast. Forecast is not just how much wind you're going to get. I was actually very pleased to see for the first time that actually our people are working right in this lab, and this is part of the kind of the ramping of my IQ, is that I understand that you're actually doing the right thing, is that translating actually wind into power, into megawatt, is another issue. It is, yes, you have a wind speed, but does just, once you have wind speed, it give you the same amount of power? Not necessarily. And I understand that there's good research on it, and I can tell you that we'll really watch it very closely. Also, it is not just how much wind I'm going to have tomorrow between the hour such and hour such, but when exactly it happens in time, so I can prepare for it for all of those load following facilities and all of those regulation is very important. So it's not just the amount in a rough way, but the exact times of it is very important to our operation. Another area of concern that we look at is something like this, where wind, amongst other things, we call them non-dispatchable. Non-dispatchable means it is not a kind of the thing that you can push up and down in shorter periods of time. In that category, you have the hydro, especially not the hydro with storage, but the hydro, the run-of-the-river hydro, that as long as there's water, it just runs. The nuclear, you don't push nuclear up and down. Well, it's kind of, it's very much base load. You have the bio, and you have the wind, and you have the solar. And there are some times in early hours where the accumulation of all of this is equal or sometimes even higher than the demand. And that's when you say, I have more energy than I need. What do you do with it? The way the market deal with it, usually you find in cases like this, you find that the prices of balancing energy in the ISO negative, meaning you pay people to take it. Now, part of the challenge that we do is we can't have too much of that. Why? First, there's a lot of time where there's no buyer, even at negative prices. I have my own, and now what am I going to do with it? That's one. But actually, even if you get someone who really can take money to take the energy, what you have done now is you pay dearly for the generation of renewables, because they're, by definition, they are more expensive. And you also paid dearly for someone to take it. A lot of time, it is actually the taking it from the generating in the same place. It doesn't even have to come to California, but it's scheduled to California. So the two balance each other, and you pay twice. And that is not right from an economic point of view. And you can see now the balance we're talking about was striking between balance, reliable. We're trying to get the system reliable, so you can't have over-frequency by generating more. And at the same time, you also, from an economic point of view, you want to make sure that the economics and the market is running properly. A case is not just the shortage of wind when people say when the wind doesn't blow, but even if it does blow, and it does blow hard. And this actually, I borrowed this from my friends in Spain. This is a case where, and you see that actually a lot. And when we get that to 20%, full 20%, then 33% overall are going to have of those. When the wind grows very hard, very high, you have to stop the turbine. You put the brake on them because mechanically you can destroy the turbine. And here is a case where it was very high, about 220 kilometers. That's like 140, 150 miles per hour. And they had to shut it. And that means sudden drop, now drop from this hour to this, of gradual of 7,000 megawatts of drop that has to be taken by other thermal plants that would have to come up to actually pick up those 7,000 megawatts of drop. So the drop in generation is not just when the wind doesn't blow, but also when it blows hard. And when. Very key, when. Because it depends on when, it will also determine when will I be able to bring other facilities to back it. Remember, many of those facilities, if you don't have them from the day before, they don't come because it's too late. Which comes from the point of we need more of the facilities of, remember I said new of the old and new of the old meaning old fuel-based. But in terms of technology, it would have to be the ones that fast start. So I can give it 1 hour kind of from here, maybe from 15 to 16 or 16 to 17, and they can come in 1 hour. Problem is, now I try to get people to say, I need more generators, gas-fired, fast to start, because without it, I can't do renewables. Very tough message, very tough message. So keeping the old one in place and even having the new one that I would need more of, and I will tell you how much more we need of that for the case from California based on the simulation we need. Now, what does that say? So we need more and need more. Now that I explained to you what is load following and what is regulation, this is the impact on the load following capacity in the 4 seasons. So I'll give you some indication when we say more, how much more. Right now, it is like, from a regulation point of view, you know, we based on the highest demand in our record, we need about 277 megawatts. On the 2012 case, that number would be 500 megawatts for regulation. On the negative side, we had the highest we had is 380. It's probably about 570 comparable. And then in terms of maximum load following requirement, it's about 30% increase in load following requirement. So you could see now that the existing fleet that we have that relied on in the past, it would generate less energy because we have renewable. Kind of, in terms of energy megawatt hours, they would produce less. But in terms of the services that they would do in the past, as an ancillary service that they would not pay much for it was just a part of the whole deal, you need them more for it than we had in the past. So that's when we say, we need it even more. And if you shut it down for, once-through cooling and the limitation for emission and what have you, yes, you save in this, but you also you hurt the other. In terms of speed, I was asked that question, how fast do you want them to do? That, by the way, that speed will, for those of you who are working on storage technology, the speed is very important for storage technology as to how they will back up together combination with the traditional generators, how they can meet that high speed. Now, in terms of speed, again, traditionally it's about 60 to 70 megawatt per minute. The 20% will increase that to about 120. There's about double. So it will go double as fast. Now, those, of course, you know that mechanically, also that means more maintenance, and some of them can do it, and some will not be able to. So I have to work, and that's what we've been working on. What are the facilities that can give us that service? And not just that, but how can I design market products that can be incentive for them to stay in business and do that stuff? The maximum load following ramping, from 150 to 170, and on the other side, it is about maybe 20% more. Now, getting into that is for the 2012 or right now. 10 years forward, which is 33%, it is massive on the national or the global scale. No one is going to that level in terms of penetration. So we are so happy and so pleased that we are in the forefront, that will be showing the world how to do it. And I actually, frankly, since then, also with the challenge, I'm kind of asleep like a baby. I wake up every 2 hours and cry. But because that's a challenge. You kind of face the challenge and said, I love it. We're going to be in leadership, leading that. But at the same time, the challenges are quite significant that we're working on. And again, for all my dialogues this morning, it looks like many of you are just hitting right on it. There's more thermal support, even more than what I've showed in the last tables, unless, and that was the unless in my first slide, storage, demand response, and smart grid in the right way take off. Now, there is a big environmental debate amongst the environmentalists, and both sides are very passionate. The so-called air green and habitat green. I have met some of the most respected people in the environmental community who actually classify themselves as habitat green. That they used, excuse me, but they used very strong words. They said, we are raping the environment. That's their word. By high penetration of renewable because of the landscape it takes from the desert and from mountains and all of that stuff, that we are replacing habitat environment with energy resources that are actually solving one issue, and in their mind they're doubting, but actually creating another bigger one, impacting the environment on the habitat side. So that debate, when you come to the 33% or those higher, that even on the environmental side, environmentalists are split as to whether this is the right way to go or not. On the demand side, there's a lot of newcomers. One of them is electric vehicle impact. And now on paper, you and I know all the benefits and all the advantages of electric vehicles. The point is it really, is it the only approach? Is it the right approach for transportation? And again, I was discussing it with some of your colleagues this morning. The electrochemical industry needs better credibility, put it this way, with the public, especially when it comes to battery. I think most of you, probably you can all relate to this. How many battery specifications of all kinds that you read and you've actually used and you found that it actually matches what you expect? Hardly. It says, 45 hours for computer batteries, and you find like probably 10, 15 hours you have to recharge. It's just like the whole cycling and the whole thing. It did not establish good credibility publicly from, especially now we're going to cycle those batteries up and down quite heavily in a usage that it has not been done before. But at the same time, really it is, you can't ignore it, it is one impact. But again, I was pleased to see it on your chart this morning, and I hope it does not go away. The fuel cells. So we were investing heavily in fuel cells, very heavily, and then it's all kind of went down, and then it was now all batteries. And frankly, the balance between the two has to be there. I think there is a room for fuel cells. It should not go down, and I hope that with all the attention to batteries because of electric vehicles and because of the energy storage on the grid side, fuel cells research does not go away. Now, what does the 2020 picture is in terms of what the impact is? I gave you in the last tables for these two graphs. Now, this is the third. What's the impact of the 33%? On the regulation side, see from 277 megawatts to 500. And if you do 33% without significant amount of storage, that would go to over 1,000. So you can see that compared to this, you need the fleet 4 times the duty. This is talking about the traditional fleet. 4 times the duty for, compared to what it is today. And if you look at the load following, it is almost double what it is today. That is what the existing fleet will have to do to support renewables. And the rest of the story, again, this is by season. From a speed point of view, it's even more compelling. You see, how fast will it go? You see it doubled here. It doubled again. It's almost like 6 times as fast when you talk about it. Why? Because for the 2012, the assumption is it would be mostly wind. For the 2020, the assumption is most of the addition will be solar because the advances in the technology of solar are not there, quite there now, even from a capability point of view, but the assumption is that by 2020, it will be there. And that's what created that demand for much higher speed in response to regulation and the load following. As we go forward, 30 years now, those of you who are 15 years and younger will have to worry about this. Now, I would suggest that you look at something for EPRI. It's called Prism 2.0. And it is looking at what would the world look like, what would the nation's supply portfolio should look like to achieve an 80% reduction of emission at minimum cost or at reasonable cost. And the answer is everything is on the table. Everything. Coal, clean coal. Nuclear, solar, wind, geothermal, gas-fired, the whole portfolio on the table. And when you get into the details of the Prism, it actually varies by region. Some regions would be more economic for them to do more clean coal than others. That if you do that whole portfolio with that mixture, which is everything on the table with varieties of percentage depending on the region, you get lower cost than what you would do with the traditional gas fire. And the key to that is they put $50 price on carbon. So if you assume that carbon will have a price, and if you pay that and you use traditional, it would be much more expensive than having everything on the table, especially clean coal. Now, from that point of view, really picking up a very narrow resource portfolio now will be wrong at best. So it's just to say that it is wind and solar is the only thing and we'll go forward with it, that would be wrong. Now, what happens if, and then you know that there's a lot of passion that's against carbon. And yes, we're all passionate about reducing carbon. But what about all the technologies of cleaning carbon? Now, abandoning coal from our portfolio altogether as a solution, as the only solution for coal, what would it do? First, the demand on coal, because we're out of the equation, so the global demand on coal would be less, and price would be probably less. So what would it do? Most of the world is in a developing stage, and they will continue to be. What they will do, someone else will burn it. And it will be cheaper because we are out of the equation, and there's more coal than otherwise. Now, if they burn it without anything, just like the old days, well, we haven't solved the global issue, the global warming issue. Or another thing is that they might develop a technology for cleaning coal. It will be in a technology and on standards that we did not own, we lost. And it is very important for all of us to think of, again, clean coal and carbon capture and sequestration is part of the equation. And it does require, not just from the North American or from the American needs, from the global need, that we get control of it, we invest in it, and we get control of it for the purpose of our portfolio and also the global portfolio. Can you achieve 50 to 80% reduction in emission nationwide, since you're a national lab, without nuclear? Again, the results of the EPRI Prism, no. Otherwise, it would be a very expensive proposition. So that's what I'm saying, 30-year plus. Again, there is issues with the storage and, the spent radiation and what have you. Those are the issues that need to be dealt with over the next 30 years. What have we done about it at the ISO? Just a very quick publicity. Transmission infrastructure is key, and I'm proud to say that every major area of renewable in the state, wind in the Tehachapi, solar in the Mojave or the Arizona, California borders, geothermal, and otherwise in the state, every one of those regions, the transmission in the main infrastructure to integrate it to the grid has been approved and to a large extent is under construction. That is more than any other place in the country. We're developing market products and services because now that we need that fleet to provide services that was not quite valuable in the past, but now we need more of it in the future, you have to develop market products and services and price it right so those people can have incentive to stay in it and actually invest to provide it. We're supporting a piloting storage technology, wind and solar forecasting. We're spending a lot of work on it. And when do we got to the point where in terms of, we got to the wind of, okay, how much wind do we have tomorrow and how much megawatts and what have you. Anyone I talked to, I was actually proud we got to the 15% or say, well, let us keep going. And then I went to Alberta, so what did you do? I said, well, we did a great job. We got to 15% and we're still going. And then I went to Spain and said, oh, we got to 15%. I said, well, it looks like 15% is the way it is, but it somehow, I don't know whether that is the end or what. We all kind of at that about the level and we're still there. And whether the way it is or it can be better, I am not sure. But certainly solar forecasting is something that is going to be very significant, and it is it's nowhere near the advances we made on wind. We are building a renewable operations center as part of our new control center. We are trying as much as possible to guide policy making, and that is harder than any technical issue that we faced or we are facing. And also, as much as possible, we try to get involved in the smart grid architecture. Now, there is no better time, frankly, for education and research than it is now. And one of the, I hope that it doesn't continue to be sad too much, is even the education part of it, not just the research. When you look at how much education cost is escalating on a student or an individual, and what we're competing with as an economy or as a technology are countries who have virtually free education. It is not getting the attention it deserves. In fact, in my mind, yes, there is a healthcare issue, but you look at the life expectancy of people and how healthy are we getting, apart from individual cases, and how well we're doing versus the challenge with getting that higher level of education in terms of cost. The latter is not getting the right attention. So I'm talking to many of you who are educators. I certainly would be one of those people who would carry the mantle with you, but there is no better time than now for both education and research. Thank you very much for your attention.